Hello, everyone. In this video, we will give a guide and tips for chapter 25 of my Java book. Chapter 25 is on binary search trees. This is a typical topic in the data structures course. Now, in the past, the preceding chapter, we looked at the implementation of lists, array lists, and linked lists. The time complexity for insertion, deletion, and search in general is order of n time. Can we do better? Yes. So we're going to have this data structure binary search tree. It will give you, on average, the order of log n time for search, insertion, and deletion. So let's look at this data structure, binary search tree. So here is, first, we know what is a binary tree. So you have two branches for internal node, and so the tree has a root, and you have the left subtree and right subtree. So this is an example of a binary tree. So the search tree is this. Look at every node. On its left, you have the values less than this node. On the right, you have the values is greater than this node. So here is another example. You have all the characters. So on the left of G, so there's a less than G. On the right, this is greater than G. So this is the binary search tree. So when you perform a search, so here, let's see, if you search for 57, you first start from the root, you compare 57 with 60, it's less than 60 going to the left, and greater than 55 going to the right. So now you have a match. Now if you do 98, so 98 is greater than 60 goes to the right, but less than 100 goes to the left, and 90 here is greater than 67, but there's nothing here, so 98 is not in the tree. So that's how you do this. On average, the trees, all these, the nodes are well spread, and the average height of the tree is order of log n. So the complexity for all this search, insertion, deletion, is order of log n time. All right, so here in this section, we look at all these terms, and now, and the next section, we look at the how you represent a binary search tree, and using the linked structure for each node, you have the left and right branches. All right, so now you search an element in a binary search tree. So this is the algorithm. So we do a search starting from the root and then comparing the value with the root value and going to left or right. So this is for search, and for the insertion, and you're going to performing the search. If you don't find the element in the tree, and then you're going to insert it at where your search ends. So this is for insertion. And tree traversal, so there's different ways to traverse all the elements in the tree. So we have the in order, pre-order, post-order, depth first, and breadth first search. So this is in the section. And the time, we define the BST class. And here we define the interface tree as a sub-interface of collection. And now define this BST as a subtype of the tree interface, and the BST contains the tree node. So here. And so this is a complete, this is the one here, is the tree interface. And And this is the the complete implementation for the binary search tree. This is implements tree. So here's a test program for this using the BST class. So now let's look at how you delete an element from a binary search tree. So first, you perform a search. If it's not in there, so you're going to return false. Otherwise, so you're going to consider two cases. These are two cases. So this is the current node you're going to delete. If there's no left child, so that's one case. And the other case is it has the left child. So what you do. So if it does not have left child, so that's simply you're going to connect, you're going to remove this current and connect the subtree of this current is right and to the parent of the current. And for this case too, so here you're going to find the rightmost in the in this node right here, and then remove it, and so connect it here. Connect this. So this rightmost is going to be used to replace the current. And now this is the left child, the rightmost is connected with the parent of the rightmost. So this. Okay, so here, and this is the test code, and this is all the illustration of the test code. And so now let's visualize the binary tree. And so here we have the binary tree and display it. So here using, and this is the so this is very, very useful here. When you test your data structure, you want to see it. So, and this visualization, it's tree visualization. All right, so here, this binary search tree is an also instance of iterable. So we're going to implement this. This here is the how you get the iterator. So we need to have one iterator. So this is already implemented in the completed code for the binary search tree. So we'll write a test code now, and because it has iterator, you can use for each loop or for each method. The last section in this chapter is a case study on data compression. So you have all using the utility zip, so compress a file. So we're going to see here how you do this data compression and using the binary search tree, binary tree. Binary tree here is, this is a Huffman encoding. So this is the encoding. It's using the tree like this structure. So we use the using the tree structure and to construct a coding tree. So this is the performing encoding and decoding. All right, that is all for this chapter on binary search tree. Thank you for watching. Goodbye.